Hi, my name is Alexander Demetrio. Today is June 22nd, 2024. I'm doing the week 5 case connections, and we did cases 1 and 2. So let's get started. Okay, so let's start off with case 1. So in the body, ammonia is produced as a byproduct of protein metabolism. It is highly toxic, so the body has developed several mechanisms to safely transport and detoxify ammonia. One key mechanism involves the enzyme glutamate dehydrogenase, which converts ammonia and alpha ketoglutarate to glutamate. This reaction is reversible and helps in the assimilation and release of ammonia depending on the body's needs. Another important enzyme is glutamine synthetase, which combines ammonia with glutamate to form glutamine. Um, Glutamine is a non-toxic carrier of ammonia and can be transported in the blood to the liver, kidneys, and intestines. In the liver, the enzyme glutaminase converts glutamine back into glutamate and free ammonia, which is then incorporated into the urea cycle for excretion. So transamination reactions where amino group is transferred from one amino acid to an alpha keto acid are crucial in amino acid metabolism. These reactions help in the redistribution of nitrogen and between amino the redistribution of nitrogen between amino acids and they play a significant role in the synthesis and degradation of amino acids. So, for instance, the transamination of glutamate to alpha ketoglutarate catalyzed by aminotransferases, it facilitates the transfer of ammonia into the urea cycle. So, in the fasted state, nitrogen transport is closely linked to gluconeogenesis. Alanine and glutamine are the main non-toxic carriers of ammonia. Alanine, which is generated from pyruvate and ammonia, is transported to the liver, where it is converted back to pyruvate by transamination. The pyruvate can then enter gluconeogenesis to produce glucose, while the released ammonia is processed in the urea cycle. So the elevated levels of urine orotic acid in normal plasma citrulline suggest a deficiency in the enzyme ornithine transcarbamylase, which is also known as OTC. And OTC deficiency leads to the accumulation of carbamoyl phosphate, which spills over into the pyrimidine synthesis pathway, which results in increased orotic acid production. The normal plasma citrulline levels indicates that citrulline is still being produced, so enzymes downstream of OTC, like arganosuccinate synthetase and arganosuccinate lyase, are likely functioning properly. And as a result of OTC deficiency, the amino acid arginine becomes conditionally essential. Normally, arginine is synthesized as a part of the urea cycle, but with the cycle disrupted, exogenous arginine is required to maintain protein synthesis and other metabolic processes. All right, let's move on to case 2. So, under normal conditions, very low density lipoprotein particles are synthesized and secreted by the liver. VLDL, which is the short term for low density lipoprotein, is essential for transporting triglycerides and cholesterol from the liver to peripheral tissues. The process begins with the assembly of VLDL particles in the liver, where triglycerides and cholesterol are packaged with apopolipoprotein B100. Once secreted into the bloodstream, VLDL particles undergo maturation. So lipoprotein lipase, which is an enzyme found in the endothelial surface of capillaries and adipose tissue and muscle, hydrolyzes the triglycerides and VLDL into free fatty acids in glycerol. These free fatty acids can then be taken up by the tissues or for energy or storage. So as triglycerides are removed, VLDL is converted into intermediate density lipoprotein and eventually low density lipoprotein, which primarily carries cholesterol to the cells. So non-alcoholic fatty liver disease occurs when excess fat builds up in the liver, not due to alcohol consumption though. It has nothing to do with alcohol consumption, which is very interesting. This condition is commonly associated with obesity, insulin resistance, and metabolic syndrome. In the case of NAFLD, there are several potential metabolic impairments. So, first off, increased lipogenesis. So, in NAFLD, there is often an increase in the synthesis of fatty acids within the liver, and this is driven by an upregulation of lipogenic enzymes and pathways, partly due to insulin resistance and high carbohydrate intake, which promote the conversion of glucose to fatty acids. Then you have impaired VLDL secretion. So when the liver accumulates excess fat, its ability to properly assemble and secrete VLDL particles may be impaired, and this can lead to further accumulation of triglycerides within the liver cells. The inability to efficiently export triglycerides as VLDL particles exacerbates hepatic steatosis, which is fat accumulation in the liver. And finally, there's oxidative stress and inflammation. So excess fat in the liver can lead to production of reactive oxygen species and oxidative stress, which can damage the liver cells and lead to inflammation. This inflammation can progress to non-alcoholic steatohepatitis, which is a more severe form of NAFLD that can result in fibrosis and cirrhosis. And these are my sources. Thank you.